Okay, so it's 10 o'clock, so let us start. Welcome back. So I'm gonna sit today. So I'm tired. I jet lag. I couldn't sleep well last night. um, uh, any question before we start? Jung, how did you send out the schedule for today? Okay, perfect. All right, so let me start. If there's no question, then I actually can start. So let me actually recall last time what we do. So last time, just a quick review. So last time we looked at a few things, right? Especially we look at the first order of the necessary and sufficient conditions. Right, for optimality. For functions from that take from us from Rn to R, and then we of course this is just the question that we wanna, and then we look at the second things, how to compute, right? The second thing that we look at is how to compute the a local minimizer. And what we do is that actually we derive, in particular, we derive the gradient descent approach. Right? So and then and we show that with in particular we update, right? We update our iteration by, you know, iteratively. That is, I think we call delta. So in general, delta is a functions of j, right? So this delta is actually j minus 1 in general, and the gradient of f as j minus 1. And then we argue, that with appropriate choice, and of course we didn't mention much about that choice of delta j minus 1, right? And then we know that j, the sequence going to converge to x star, where x star is a local minimizer. So that's actually the key that we do last time, especially the last hour. Any question? Okay, so if not, then we're gonna do today, our schedule for today, we're gonna do, I think Professor Chung Hao already sent you the schedule, but we're gonna show the conversions, the conversion of gradient descent method for strongly convex functions. So we look at the easiest case, which is make us the key to understand, right? And then we actually, like I mentioned to Professor Chung Hao, I'm going to change the order a little bit. Instead of going to probability theory, I'm going to go to deep neural network, right? I think that's a better idea, because at least you're going to see it, and then you see the need for probability later. So I'm going to do a very, you know, elementary introduction to neural network or deep neural network. And then we're gonna try to show that the question that we're gonna ask ourselves is that, right, is or are neural network. That's good, right? So our question is very simple. Is that good? Can it approximate any functions, right? Because the key is actually a neural network. At the end of the day, you're gonna see that we're gonna neural network try to learn some function, right? Try to approximate some functions, and can it do that? And in particular, we're gonna look at the universal. Sorry, universal theorem for one particular neural network, which is ReLU, which is a rectilinear function unit, rectilinear unit, and this is also known as ReLU. Okay, and then I don't know, depends on our time. If not, we can wait until tomorrow, and then we talk about we back to how to train. Right? Of course, I'm gonna introduce you what I mean by training later. Training deep neural network with a gradient descent via back propagation. So we're gonna introduce what do you mean by back propagations and how we actually see it, right? Propagations. Okay, so that is our plan for today. Okay, so we're gonna try to do as much as we can, but we're gonna do what the we don't have to go very fast, right? The key is to, like I said, the main point is to give you, sufficient rigorous enough, and also a starting point so that you can use it, right, to actually do more advanced stuff later, right? And this is important to have a, strong foundation for the easiest thing first, and that is our goal. Any question before we start? No? Okay, so let us dive into the lectures. So we're gonna start with the first topic, which is conversions of the gradient descent. So you need to see at least once, okay? We don't have to remember it, but at least you feel comfortable. You see at least one, the thing that we use, gradient descent and path converge, at least for under which conditions, right? The simplest conditions, conversions. Okay. All right. So we need to, in order to do that, we need to start, introduce a couple of things. So I assume you know what convex means. Okay, so if not, please check. Okay, please check later, but I'm gonna go to the definition anyway, so that you can see convex set. Just start from the simplest thing first. A set X in R, a set X as a subset of Rn is called convex. If and only if I double F, or even only if for all X and Y in X, and any number alpha between 0 and 1, we have we have the following. We have that alpha x plus minus alpha y also belong to x. So this is also known as, convex combinations of x and y. Okay. So if you pick two points in the set and then you just do an arbitrary convex combination, and this is still in the set X, and also X and Y arbitrary, right? Then the set is convex. So that's the um, um, the definition. Of course, right? A consequence is it is clear that the whole sequence, by definition, the whole segment, right? The whole segment, a whole segments between X and Y belong to X. If X and Y belong to X, therefore convex sets. Okay, now that's a convex set. For example, right, you can see, if you take a circle, that's a convex, and then you can take a square as well, right? Any polygons, convex polygon. So these are convex sets. Now we next move to definitions of convex functions, because we have people, student from undergrad student here. So we do just, make sure that we recall on the definitions first, and then we go to the theorem immediately. Okay, convex functions. First, we let x be a convex, right? Convex subset of Rn of functions of function f from x to R is convex, even only if for all x, y belong to x and any alpha between 0 and 1, any alpha between 0 and 1, we have the following f, right? You actually, what do you do here? You take a convex combinations of x and y with, I'm sorry. We take a convex combination of x and y, and we also look at the function x. I'm sorry, not function, the value of x and y. So these are three vectors, right? We know that the convex combination of x and y also belong to x. So what we are interested in is we're going to evaluate, right? We're going to evaluate f at this point, and we're also interested in evaluating f at these 2 points. If the function is convex, then we have something relationship between these. Do we remember any of us? Can any of us remind the rest of the class? What is the relationship between the function evaluated at the convex combination of x and y, and then the function evaluated at x and y? Any of us volunteer? No? So shy. I used to be like that. Okay. Uh, last chance. No, you don't want to take a last chance. Okay. Okay, that's fine. Then we continue. Less than or equal to alpha plus 1 plus alpha, right? So basically it's this, right? If you look at 1D, so we look like 1D here, just, intuition, some intuition here. And this is, let me call this is X. Our X is here, and this is F. Of course, X can be here, right? You can think about this axis is a space, right? It doesn't need to be one-dimensional. And then our function is convex. If I take a point X, right, this is a point X here, and then a point Y here. So I have two vectors here. And then I'm sorry, I think I should, this is happen to be on the same level. Okay, let me move actually a little bit, maybe here a bit better. So X is here, and we see a couple of things, right? So first, the line segment. Remember, this is the line segment between X and Y. And then if I take alpha, right? So we do two things. So we look at alpha. So this point is alpha, right? Alpha X plus 1 minus alpha Y, right? In between, right? Convex combination, so it's in between one point particularly. And therefore you see that our function is here, fx values, and then of course this is f of y, right? And then of course now we have alpha plus we have now alpha x plus 1 minus alpha y. Oh, I'm sorry. Then our function values is here. Okay, so this is f of alpha x plus 1 minus alpha y. Okay, so the definition of convex function is the following, right? So I'm sorry, I put it wrong. I'm sorry. I make a mistake there, everybody. Okay, I make a mistake there. I'm sorry. Not on the way up here. Okay, because we evaluate the function, so it must be here. I'm sorry. So the graph is a little bit crowded, but let us try our best here. So right, this is f of alpha x, because that's the point, right? The function evaluated alpha x plus 1 minus alpha y. So the intuition is this. And of course, right, of course, this point, because by similar triangles, right, by similar triangle, I know that this point is alpha fx plus 1 minus alpha fy by similar triangles. Okay, so what we see is this, right? If the function is convex, then you see this is a convex combination of x and y, and then it's the function values. That at that convex combination, it must always be below, right? It must be below the convex combination of the function evaluations. Right? This is the convex combination of function evaluation as 2 point x and y, right? This is the functions evaluated as a convex combination of x and y, right? If the function is convex, then this must be below this. That's the iterations. Everybody see that? That's not graphically what it means by convex functions. All right. Any questions? Okay, if not, then we actually move next. We immediately have this lemma. I'm not gonna prove it, right? You're gonna see in the lecture notes. So we have immediately the important lemma. Of f is convex if and only if f of y greater than or equal to f of x plus the gradient of f evaluated at x, and then this is y minus x. So this is actually quite clear as well, right? And this basically say this. Right? Okay. So you see, what is it here? By the way, on the right-hand side, what do we see? The right-hand side is what? what is intuition on the right hand side? This is the first order of Taylor expansion, right? What does it say? This is what is it, the right hand side? The right hand side is a linear approximation of the function at point x. Everybody see that? The right hand side is a linear approximation of the function at point x. So if the function is convex, so let's do it again, our thing here, which is our convex here. And then if we pick a point x here, right? And this is again, this is our x here. If the function is convex, then this one is f of x plus gradient of f x dot. I'm sorry, this is dot, right? Because vector, you see that the gradient is now a vectors. And this by itself is a vector in general. So there's a linear approximation of a function at point x. If the function is convex, then you see that at any values, the function is higher, right? See that the function itself at any value or the function is always higher than the linear approximation. This is what it means, right? Everybody see that? So, or it doesn't say, basically, you know, intuitively, we're gonna use this as well. Everybody look at this, right? Fy is less than, but this is not intuitive. Plus gradient of f x dot with x minus y. We're gonna use it later, okay? But it's just I multiply negative both sides. Everybody see that? I just multiply by negative both sides. But this, the first one is important because what it says is that the function is convex, then the functions is always above, right? Always above the extensions at any point. Extensions at any point. We just show it, right? So that's the intuitions. So in the sense, it's not, and you see that the proof is not difficult. I mean, and I'm going to skip it, okay? For the sake of time, the proof requires the definition of directional derivative, okay? So and you see it's very easy. I'm not going to go through it, but the intuition is very clear. If the function convex, then it's going to be above, right? Going to be above any tangent at any point, at any point. At any point, you see that at any point, right? The function is above the tangent at any point, regardless. Okay, so now we actually go to the main theorem. Any questions? Okay, so we're gonna go to the important theorem that we are looking for. I'm gonna suppose that f from n to r is convex, and differentiable. Okay, that's the first conditions. That's the first condition. Second, we assume that it's Hessians. The Hessian of f, the Hessian of f, the Hessian of f at any point x. The Hessian is a matrix, right? This is a matrix induced matrix norm. Okay, so this is the norm of the Hessians, which is by definitions. You know, I hope that you know what it means, but if not, then let me record it here. It's an operator norm. It's an operator norm, right? Multiply dot with y, and this is in a norm. This is L2 norm that we are talking about now, L2 norm, and then y. And you take the supremum over on y in Rn. And we assume that it's less than or equal to L, right? For any x in R, in Rn. So this is where we assume it's a strongly convex, right? Because we assume that Hessian, the curvatures, think about Hessian is a curvature, right? the curvature is bounded by a number L, capital L. Let me rewrite that a little bit. Let me rewrite that a little bit L here. So for some L that is greater than 0 and for less than infinity, the bounded value. Okay, so F is convex and differentiable. Assume that the Hessian or the second derivative, right, the norm of the Hessian matrix is actually bounded above, and then we run if we run the gradient descent with a fixed step size, right? So that means delta J is equal to delta, which is what we used yesterday, right? And as soon as it's less than 1 over L, as soon as the step, the gradient, right? Remember that delta is the step in the negative gradient. If it's less than 1 over L, then we have what? We have this. We have f, the function evaluated at xj plus 1 at the j plus 1 iterations minus f of x star, which is a minimum, right? Which is the global minimum, is less than or equal to xj, x0, I'm sorry, the initial, minus x star. And on a norm in the L2 norm, right? To delta to delta k. I don't know whether I may make a mistake here. We come back later. Okay, don't worry about it. So square. So actually, let me actually make sure that we understand this is the L2 norm. I put a 2 here. Okay, 2, where fx a d, because for convex function we have only one, especially the optimal values, ad minimum. We skip that, okay? So I encourage you to look at any convex optimization book. If the function is convex and differentiable, right, in particular, then there's one single global minimum, right? And this is the one that we are talking about, single D global minimum. D, or global minimum. Okay, so let's look at it again, right? So f is convex and the second derivative is bounded. Then we run the gradient descent with fixed step size, right? So to answer your question, we're gonna that step size how it look like, right? If we do a fixed step size like that, we sure that it's gonna converge. Okay, so let's see how we're gonna go about it. Any questions? Okay, proof. We're gonna start with by Taylor expansion. You see that? Taylor expansion is our best friend by the Taylor remainder theorem. Remainder theorem. We have f evaluated as y is equal to f. Around x, we expand our function around x. Plus gradient of f on x dot with y minus x, right? And then we have a second order term, which is 1/2 of y minus x, transpose, and then time the Hessian of f. adds some z, and then this is tangent here, and then y minus x for some g in on for some z on the segment x y. Okay, so remember, right? It's very similar to what we showed last time. We can stop the Taylor expansion here, but we have to evaluate as a point z. I'm sorry, I'm going to put the vector, right, on some point, right? There exists a point in between x and y on the segment such that this holds. So that is a Taylor remainder theorem. We don't use anything particular difficult here. Okay, now notice that I'm going to take the absolute values, right, of y minus x. I'm going to look at this term. I'm sorry. I'm going to focus on this term. I'm going to bound this term, right? Remember, why do we need to? Why I'm looking at this one. I'm looking at this one because we have the condition on the second derivative, right? It's bounded. Okay, the second derivative is bounded. So I'm going to look at the second order term because we can replace the second derivative with the bounds in the assumptions. So that's why we look at that one first. The easiest term. This is the easiest term. We're going to look at the easiest term first, right? Absolute values. This is less than or equal to. This is less than or equal to y minus x. L2 times the Hessian of f at z times the vector y minus x. What did I have just used? What did I have just used? Cauchy-Schwarz, very good, right? So I just use Cauchy-Schwarz inequality. So I had just used Cauchy-Schwarz. Very good. Okay, and then this in turn is less than or equal to. This is less than or equal to. I rewrite the first term. Y minus x, the L2 norm, and this is the Hessian of f at z, L2 norm, and then y minus x. What did I have just used in order to get from here to here? So I keep this term. Everybody see that? I keep this term. But this is less than this. What did I have just used? Hmm? That's correct. That we just use the definition of the norm of the Hessian here, right? So the supremum. Remember, this is the norm of this guy is a supremum of this one. So of course this is less than this times this, right? This is less than this times this because this is a supremum. Okay, that's exactly very good. Very good. This is just the definitions of just use the definition of the the L2 norm of the or the induced. The correct word, the correct terminology is the induced 2 norm of the matrix, Hessian matrix. All right, good. So now I'm gonna do this next, right? This is in turn is less than equal to y minus x, L2 square, and this is L. And this is obvious, right? Because we use assumptions. Because the assumption that the induced norms of the Hessian matrix at any point is less than or equal to L. Okay, so what we have is this. What we have is this. Sorry. So what we have shown is that maybe I just therefore we have shown that the I'm a little bit lazy. Everybody, so I'm gonna do this instead of rewrite it. So we have shown that this term is less than or equal to this, right? So that's what we have shown. Okay, good. So we eliminate the Hessian or the second term, right? So we just bound this term already. Good, right? And we still have to deal with this term. Remember, right? Remember that we need to look at this. Our final result does not have Hessian or gradient, right? So we already remove this. We somehow need to eliminate this part somehow, right? In order to get to the final result up there. So that is our goal. Any questions so far? Any question, please don't hesitate to stop me if you have question, okay? Any question? If not, let us continue. Let us continue. The proof is, a little bit long, but it's very easy, not difficult. Okay, so that's right. That's let us summarize. Right, we have Fy is less than or equal to f of x plus gradient of f of x dot with y minus x plus L y minus x square, right? So I just show that, which is good. Now we're gonna continue. Right now, take, and you can see, right? Y, we're gonna take y as, because we at the end of the day we need to connect with j, xj, and xj plus 1, right? Take y equal to xj plus 1 and x. That's the result there, right? Inequality there is valid for any x and y. Now we're going to pick two specific x and y, right? Which is the iteration of our gradient. We take a two specific values of x and y, all right? So if we do so, then we, let's just write one more time. F of xj plus 1 less than f of xj plus the gradient of f of xj, and then xj plus 1 minus xj and plus L xj plus 1 minus xj square. Okay, now we're gonna use gradient descent, but right, this imply because in the gradient descent we have xj, right, by gradient descent iterations. We know that xj plus 1 is equal to xj minus delta gradient of f of xj, right? So that's what we know. We're going to do a substitution in there now. Okay. So xj plus 1 minus xj plus 1 minus xj going to be the negative of delta gradient, right? So this dot with that become negative delta of the gradient norm square. Everybody okay with that? So the first term we immediately have is, therefore we immediately have that this is equal to fxj plus 1 less than or equal to f of xj minus delta of gradient of f of xj square, right? So a vector dot product with itself is the norm square. So we're done with that. We also have this. We also have this. Xj minus or plus 1 minus xj is delta greater than f and square. Okay, so we have delta square. L times exactly this term. So we're going to do substitution in there. So we have plus. Oh, I'm sorry, there's a half here. I forgot, but everybody. Sorry. Okay, that's a half because of Taylor expansion and half there. So there's a half here, and now plus L delta square over 2 of the gradient of f xj square. Everybody okay with that so far? So far, so good? Is that good? Yeah, I simply substitute xj, my plus 1 minus xj equal to this into here and into here, right? I substitute here, I get here. I substitute in here, I get here. Any mistake? I may make mistakes. I make mistake all the time. But anything wrong? Okay, if not, then we continue. Now we can combine, right? We can combine. We can combine. We can combine that this imply that this imply that f of xj plus 1 is less than or equal to f of xj. And then now it's just, group thing together, okay? 1 minus L delta over 2 of t of delta, I'm sorry, delta of gradient of f of xj. Everybody see that? I just combine these two terms. I just factor delta out, right? Factor delta out. And on purpose, I factor a minus, right? Minus delta out. These two terms. So hopefully I don't make any mistake. Then let us continue. Then this imply because, right? Notice that since we assume that our fixed step is less than or equal 1 over L, right? Then since we have you check this for me, please. We have that minus 1 minus L of delta over 2. Of course, right? This is less than or equal to negative 1 half. Okay, so check on that, please. Actually, maybe I do one more step for you to make it less magical, right? It look magical, but actually it's not. This is equal to L delta over 2 minus 1, and this is less than negative 1 half. Actually, it's easy, right? Because here, see that? Because delta less than or equal to 1L, 1 over L. Delta times L is less than or equal to 1, right? Therefore, the L delta over 2 is less than or equal to 1 half, right? 1 half minus 1 is negative 1 half. Everybody see that? Good? Okay. I'm sorry, I don't speak very loud today. I'm a little bit tired, okay, of the jet lag. It's not that I lose my interest in talking to you. It's just that I try to preserve some of my voice. Okay. All right. So let us continue. So if I do so, then that's less than negative 1 half, which is good. Then of course. Okay, you see that, right? This is less than negative 1 half. So that's going to be less than delta over half, like negative delta over half. Therefore, f of xj plus 1 less than or equal to f of xj minus delta over 2, right, of gradient of f xj. Okay, good. We're almost there. We're almost there. We're almost there, everybody. So we are so close. So far we use what? We use the strictly convex, right? We use three things. Let us remind what we have done. We use that the Hessian is bounded by L. We use that the time step, right? The step on the gradient descent, and we use gradient descent definitions, and we use the assumption that our step is less than 1 over L. Then we get here. We get here, but we still we're almost there. We're not quite there yet. All right. Any question? All right. So a couple more steps and we're done. Now, sorry. Now, right? Now, since f is convex, right, by the above lemma that we didn't prove, we have that f of x j is less than or equal to f of x star plus the gradient of f of xj dot with xj minus x star. Remember that we have two things, right? Let me go up there. Let me go up there and then show the lemma again. The lemma say that our functions is always above extensions, but by multiplying negative both sides, we also have this. Basically, just switch this, right, and then switch this inequality. So that's exactly what we do down there, right? We use this as an xj, x star, xj, x star minus xj. Everybody see that? xj, x star, xj, xj minus x star. So we just apply that. We get this. Okay. The reason we do so is that we're gonna do substitution in here, right? We're gonna put, because we want to eliminate fj, right? We want to have only one x, and then we need to sneak in fx star, right? Remember that we have to get to fx star. Look at the results. The result have an fx star. So now we put in x star, fx star, and we have fx star here as well. So we have to put x star into there by using convexity. Okay. Now we just do substitution. So now combine these two together. Now I'm combine this. Right? I combine this. What I get is the following. We imply if we combine these two, we get f of xj plus 1 going to be less than or equal to f of x star. Right? We replace f of xj by f of x star plus gradient of f. Gradient of f xj dot with xj minus x star, and then minus delta over half of xj. Okay. Okay, so we got here and ready. So we almost there. Okay, we're quite close. So how about this? We take a 10 minutes break, and then we see each other at 11 o'clock. All right. So I see you in 10 minutes. Okay, so it's 11 o'clock. So let us restart. Okay, so we have get here. We have get here, right? That box is what we have to get to. Oh, I'm sorry. Let's see here. Okay, remember that we only remember that the guideline for us is the results. the result there, right? The conclusions does not have the gradient, but we still have the gradient here. That we still have the gradient there, right? Everybody see that? We still have the gradient. But the good thing is that, you see this is like gradient square, right? The gradient square, and then the gradient dot with something, right? Does it remind us something? Does it remind us something? So if we have A plus B, this is elementary, right? We know this. A square plus 2AB plus B square. We know this, right? But if you have A plus B, two vectors, 2 square, right? It is equal to what? A plus B or dot or transpose have A plus B, right? Right, two vector. And then we can have similar thing as well, right? We also have similar thing A norm 2 square plus 2A dot B plus B vectors square. Okay? So when we look at this, we remind us, you see that, oh, this is something like square, and then this itself multiply dot with another one. So we're going to complete in square. We're going to complete the square. So we use very elementary tool. We're going to do a complete in square. But before doing that, let us just, rearrange things just a tiny bit. So I'm going to move the fx star. So we're good with fx star. So we move the fx star on the other side. Minus f of x star. Okay, and then I'm gonna factor 1/2 of 2 delta or 2 delta out. If I do so, then what I guess is this 2 delta of gradient of f evaluated at xj dot with xj minus x star minus delta square gradient of f xj square. Okay, so you see that when I factor 1 over delta, 2 over 2 delta out, you do see now, right? You do see this form. You do see this form, right? Delta square, of course, I'm gonna take the minus side outside as well. Then I'm almost done. Okay, so in order to complete square, I need to add and subtract. What should I add and subtract, by the way? By using this. In order to complete the square, I need to add and subtract. What? Okay, so what should I add and subtract? Add and minus or report, right? In order to complete the square, I need to add and subtract something. Can somebody help me? What should I add and subtract? Because if I add and subtract, I actually can eliminate, right? Remember that we want to eliminate the gradient here. So if I add and subtract something, I complete the square, I actually can eliminate gradient. So that's the bright side. What should I add and subtract? If I have this, right? If I have this, if I have only this, then I add and subtract b squared. Everybody see that? So what should I add and subtract? You are so shy. Is it obvious or is it difficult? So that's actually my question. Okay, so if you don't say anything, I'm gonna do it. Okay, so I'm gonna add and subtract now. So this e equal to, right? The right hand side equal to, by add and subtract x xj minus x star square, right? You just add and subtract this guy in order to have in order for us to complete the square. So if we do that, then on the left-hand side would be equal to 1 over 2 delta of what? Of xj minus x star square minus xj minus x star square. And then I'm gonna lazy, okay? I'm gonna copy this over. And this term. Sorry, maybe do this. Okay, so we just add and subtract, nothing difficult here, right? Okay, and you see that this together with this and this is equal to what? If we look at this, it is equal to what? It is equal to what? So I'm going to rewrite this a little bit. I'm going to keep the first term intact. The rest of the term is equal to what? Go ahead. You wanted to say something? Yes, please. A minus b squared. Okay, what is A? What is B? So I think this is what you mean, right? This is what you mean. This is what you mean, right? Because this is just A. Doesn't matter which one is A, right? Which one is A? This is minus A squared, right? This is plus 2AB, and this is minus B squared, right? I just have the minus here, of course. I should do this as well, right? If I have minus here, and then this become plus and minus. And if I have a plus and minus here, then I have plus and minus, right? And then I have a plus and minus here. So our case, we have a minus, right? Inside as well. So very good, thank you. So what we have is that by completing square, we have xj minus x star, right? X star, which is our a or b, whatever we wanted, and then minus delta gradient of f xj. Everybody okay with that? By just completing the square, that's what I get, right? Okay, now I'm actually moving a little bit. Notice that this. Now you need to know that. You must know this. What is this equal to, by the way? What is this equal to? You must know it. What is xj minus delta gradient of f at xj? I need an answer. What is it? xj plus 1, right? Xj plus 1, very good. Right, this is xj plus 1. I need to force you to talk somehow, right? Okay, so this is 1 over 2 delta of xj minus x star. Okay, so you see that we almost there. We actually now completely eliminate by the grade by using the definition of gradient descent, right? We completely remove the gradient, which is very nice. Okay. So in conclusion, right, we have shown that f of xj plus 1 minus f of x star is less than or equal to 1 over 2 delta of xj minus x star square minus xj plus 1 minus x star. We're actually quite close. We are quite close. Look up. We're gonna look up here a little bit. We're quite close. Look at that result that we want to prove, right? The result that we want to prove, we don't have xj or xj plus 1 or xj plus 1 here, right? We have x0 and we have x star. And the left hand side, we already have this. But on the right hand side, we have something not what we want. See that on the right hand side is not what we want. So, but on the other hand, you see that's interesting, right? This is xj and then minus. These two terms are identical or look exactly similar. The only thing different is that this is j plus 1, right? If I sum them up, so this is valid for any j. Everybody see that? We have shown that this is true for any j, right? If I sum up on j, you see that we have a telescope cancellation, right? Telescope calculations. Then that's where we eliminate j. Okay, so let's do that. Let's do that. Or right, or this imply that let me do a little bit slow so that you can see, right? F of x1 minus f of x star plus on 1 over 2 delta of x0, right? When I take j equal to 0, this is what I get. I'm sorry. How about this? Actually, let us do this so that you can see a little bit better. I'm sorry. And it's also faster as well. When I do copy and paste, okay? And then you will see it better. Hmm. Hmm. Okay, so let me redo it. Okay, copy. Okay, I'm gonna paste now. So now I apply when I take j equal to 0. So do you agree with me? This become 1, right? And this when j equal to 0, this becomes 0. This become 1. Okay, so I think that doing this is much better. And then we apply again. We apply that inequality again for j is equal to 1 now. When j equal to 1, this is equal to 2. Everybody see that? J equal to 1. This is going to be equal to 2. Okay? Now dot, right? We put this down here. Okay. Now just sum them up. If I sum them up, you see, right? You see that if I sum both sides together, right? Then you see that this cancel with this. This cancel with this. So when you look at the new inequality, right? Inequality, then the first term is canceled by the previous guy, right? So the first term will be canceled by the last term of the previous inequality. So this, and when I add they together, I know this cancel with this cancel with this is going to be canceled out. What I have left is this and this. Everybody agree with me on that? Good. Okay, so let us continue. Let us continue one more step, and then we done. Okay. Okay. Let me see here. Make sure that everything I do is correct. Okay, that's good. So now adding together or adding on the inequality together we have we have that on the left hand side, actually the right hand side is clear, right? The left hand side, you see that we have a sum of these, right? We have a sum of everybody's. So we have a sum of f of xk plus 1 and f x star k from 0 to j, okay? On the right hand side, what we have is, remember that we everybody is on the term actually cancel out. What we have is this. The first term there minus xj minus 1 plus 1 x star. Okay, so sounds good. Everybody see that, right? So we have that first term minus this last term. So that actually, we see that we have xj plus 1 here, which is annoying, right? Because we want to eliminate, but it's not easy, right? Because square minus something, then it's of course less than this one. You are positive and you minus some positive, you're gonna be less than yourself, right? So this is gonna be less than or equal to 1 over 2 delta of x0 minus x star. Everybody okay? Right? Everybody okay? All right. All right. So so far so good. So far so good. The another thing that actually I should have mentioned, right? Um, where actually let me go up here. One of the thing that we want to, one thing that I should have. Oh yeah. So we see here, right? This is important. I put the the red box there, right? Actually, it tells us something. It tells, you see that? The interesting thing that I didn't say about that, I'm gonna put some words here. You see that by doing gradient iteration, our function actually decreases after every iterations. The function evaluated at the new point is less than equal to the function evaluated at the previous point minus a positive numbers. So the gradient descent unsure unsure by choosing the delta this way, we ensure that every step we actually decrease the function. Everybody see that? Our function is decreases every iterations. Is that good? And this guy less than this guy minus this guy, of course, this is less than or equal to f of xj. Actually, let's go up there. I have an allergy with the Taiwan weather and atmosphere. Let me, where is it here? Sorry, I moved so fast here. What's the box? Okay, okay, here, right? Of course, this on the left, the right-hand side itself, because the second term is positive. The second term is positive, so this is itself less than f of xj. Everybody see that? So what we conclude here is that, you know, the function decreases, or the gradient descent. The gradient descent. We imply, right, that inequality imply that take us downhill. Every iterations. Good. Any questions? Oh, okay. So we use that fact here. We use that fact here. Okay. We use that fact here for the last. We done. We good with the right hand side. The right hand side now have x0. Remember, x0 is fixed. We pick the x0. We pick the initial guess. This is fixed. This is fixed. So this is fixed term. Good. And delta we only choose also fixed. What we look at here is this. This is f of xk minus 1 minus f x star, right? When we sum them up. So because the function decreases every iteration, right? The last guy, f of xj, actually, let's look at this. Because the function decreases every iteration, this minus this is smallest compared to all these. Everybody see that? Because this is fixed. And this guy, f of x2 is less than f of x1. F of xj minus 1 less than f of xj. And in turn, this is less than this and less than this. So this guy is the smallest. Everybody okay? So this is the smallest. So I'm going to look at here. I'm going to look at here. In this sum, the last term is the smallest term. Right? If the last term is the smallest term, then we know, right? We know that this is going to be greater than or equal. Because then I just simply take each term. Because since, actually, let me actually write that, right? Since f x j decreases at every iteration. Okay, so we have the sum of f x k plus 1 minus x f x star. Okay, this is k from 1 from 0, right? From 0 to j, k from 1 0 to j is greater than equal to f of x j plus 1 minus f of x star. And from 0 to j, how many numbers? Is it j is correct here? Is that correct? Each of the guys, each of them look greater, right? So on purpose, I make a mistake, okay? So actually, I put here. So how many term here, by the way? How many term here? How many sum man here? How many terms? How many sum man? How many of this in this sum? J plus 1. That's correct, not j. And each of them is greater than this. So the sum is greater than j plus 1 here. Okay? Everybody okay with that? Every term on the sum is greater than this. So we have this one. Okay, so combine these two together. So now I simply combine these two together. What I have is this: a j plus 1 times f of x j plus 1 minus f of x star less than or equal to 1 over 2 delta times x0 minus x star. Okay? Or this implies that f of x j plus 1 minus f of x star less than 1 over 2 delta times j plus 1 x0 x star 2 square. Or, this is also implying that when I take, because it's true for on j, right? This is true for on j. This is true for on j. So therefore, it's true for xj as well, right? Which is minus of x star less than 1 over 2 delta of j. x0 minus x star. Because it's true for on j, so I simply take it is equal to j plus 1 equal to j, right? Then I have this. So that our final answers. Should rewriting, and this is must be true for on j, right? Equal to 1, dot, 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 dot. Everybody okay on that? Right? So we have this sum is less than this. And that sum, which is here, is greater than this, right? So therefore, this is less than this, which is what we have here. And then we divide. And then because it's true for on j, I simply take j plus 1 equal to j. This is also true. Good. So we're done. We're done, right? So this result says that because this is fixed, delta is fixed, j running. So as you run the iterations, f of xj, right, minus f of x star is bounded by this term, and this term converges to 0. Everybody see that? This is fixed. This converges to 0. So our gradient descent actually indeed converges, right? Good. So this actually give us two things, right? So this is give two thing remark, right? There's a two remark here first, right? We immediately see that f xj converges to f of x star as j approaches infinity, right? As you run your iteration and more. Second, this inequality not only tells us that, but also tell us more. It's more than the rate, the conversion rate as well, right? Conversion is one thing, conversion rate is actually more difficult, right? So we actually, by doing that, we also have the conversion rate, right? The conversion rate is this, 1 over delta, 1 over j, right? So in other words, right, we also show that, oh, in fact, f of xj minus f of x star is an order of 1 over j. So it's a linear convergence. So linear convergence. By this is a big O notation. Everybody okay with big O notation? Okay, so this is big O notations. Big O notations. So this therefore the conversion rate is linear. Of gradient descent is linear. Any questions so far? So that's the two remark that we have for our result. So what I want to show, what we have tried to show is that, at least once for all, right? You have seen how to prove the conversion of the gradient descent, right? You feel confident now, hopefully, when we apply that for training your neural network, right? Because behind the scene of neural network is the gradient descent. There's a stochastic term in front. You make a little bit stochasticity. We're gonna talk about that later, right? But the main thing is this, which we should, right? Hopefully, I provided you the rigorous results on why gradient descent works. Any question before we move on to the next thing? Okay, so I'm gonna send this to Professor Chung Hao later, right? Now I'm gonna move to the next things, or maybe some of you still writing. I'm sorry, not sure you're still writing or not. Some of you still writing, so I let it wait for 1 more minute. So it's very easy, right? Convexity is the key. Gradient descent iteration is the key. And another key things is the step size, right? The step size, at least we show the result for fixed step size, right? Any step size, let's go up here. Let's look at the result one more time. Let's look at our result one more time. We assume convexity, we assume that the gradient, the Hessian is actually bounded, right? And the step size is fixed. Not only fixed, but it's also less than 1 over L, right? So theoretically, we have this, right? If you have these three conditions, we have convergence. But I'm sorry, this is J, I should put, I'm sorry, there's a typo there. There's a typo there. Let me go and fix. And this is true for on J's, right? J is equal to 1, dot, 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 dot. Okay, so of course, in practice, we don't know L, right? L is a difficult things. So I let you look more into detail on how to actually, in actual practical situations, how we actually choose the um, uh, delta, right? Because in practice, you don't know this. So I would like you to actually look into the gradient descent or stochastic gradient descent and literature to see how we choose. In fact, later on we get to the stochastic gradient descent, we're going to talk about the choices as well. But we need to realize, right? Realize that this is not practical because we don't know. And another remark that I want you to talk here is that, and I want you to do it for different exercise, okay? Another remark is that we show the condition on the Hessian's house lies so strong, right? Show that if the gradient f ellipses with constant L, that is that is gradient of f at any x minus gradient of f any y is less than or equal to L. This is Lipschitz continuity. Then the Hessians. This is all x, right? Like this is a global Lipschitz for all x and y. Then L, right? For all z inside n. Well, f of Lipschitz and of course f differentiable, right? This guy is also need to be differentiable so that the second derivative is this. So you don't need to assume this. All you need to assume the Lipschitz continuity of the gradient. If you have a Lipschitz continuity of gradient, you automatically have this. Okay, so that's a homework for you. That's homework for you. This is L2. Okay, and would like you to also, right, see that del equal to delta J equal to delta less than 1/2 a not practical, right? Because we don't know. L in general, right? Check, homework for you. What should we choose? Delta J in practice. Okay, so I would like you to Google a little bit. It's not difficult, but I'm not going to tell you, okay? I'm going to ask you to do it if you're interested. That's a little homework for you. It turns out that we don't need to know L, right? And we still have a method working. Okay, everybody, any question before we now actually move to the next thing? Okay, if not, then we're gonna go to new network, okay? So the new network is gonna be we're gonna do a slideshow. Some of you still writing, so we're gonna wait for 1 second. Okay, so let us move to the next lectures. So this is gonna be slide. I already have this slide, so we're gonna write less. So this is a new network, okay? So let we recall. Oh, I'm sorry. I'm gonna do the slideshow. How do it with view? So single page. Okay. So, oh yeah, good. So what we're gonna do, we're gonna show that deep learning is just one particular approach in machine learning. Okay, like we mentioned before. So let's look at the classifications. We didn't mention about classification, but now we can talk about that. So like what I wrote there is in supervised learning, right? We don't have the functions f. We know that the function f map from x to y. That's all we know. And for classification problem, or for regressions, right? Regression, the output of f, which is fx, is real values, right? Or vectors. But in classification problem, the y, right, is typically discrete. And for example, binary classification, 0 and 1, right? So fx can be either 0 and 1. Thinking about, I want to classify, animals photos, right, and human photos. So only one, two category. But, that's not important. We're going to look at the for the regressions for the so actually this is actually a little bit misnomer, right? Because logistic regression is actually not quite regressions. It's actually is classifications. Okay, we're gonna see that later. Okay, we're gonna see that this function later. But this is the well-known sigmoid function. So that is sigmoid function. We're gonna look at that later. But I just have introduced to you what classification means, right? And a sigmoid function. That's the main point for this slide. What is a sigmoid function? This is how it look like, right? Sigmoid function is 1 over 1 exponential of minus z. That's a called sigmoid or logistic function. Now we're going to look at a little bit of biological motivation for neural network. Okay, this is biological motivations. So this is actually our human, right? Our human neuron, one neuron, right? One neuron actually have a lot of things there, right? The key thing is that the dendrite is the one part of the so dendrite going to connect with other neurons, okay? And then the neuron itself have nuclear and then the axon. So what the neuron in reality does is that when there's a potential difference in electric signal, right, between the input and the output of the neuron is over some values, the neuron actually fire, right? When it fires, actually it sends signal through its axon, right? And then it's gonna these actually connected to the dendrites of the other neuron, right? So when there's a potential different over than some threshold, then the neuron fire or send information to its dendrite to the other neuron. And again, similar for the other neurons. So that is a biological situation in our brain, right? So that's what it is in neuron. How to model this? How to model this, right? So this is how people model the neuron. So we haven't seen real biological. What it does is that this is, remember these are only dendrite, right? It takes signal from the other neurons. This is a signal from the other neuron. It multiply by the numbers. Okay, so each dendrite take in, take the output from the other neurons as input, multiply by weight. Right, so this is connecting to the zero neuron. This is our neuron now. This is connecting to the first neuron and so on and so forth, right? So this is a simple possible mathematical model in the neuron. So what you do is basically R5 combinations. See that? R5 combination of the information. So X0, X1, X2, so on and so forth, input or the output from the first, the second, and the third, and so on neurons. What you do is that we do an R5 combination here. See that? Multiply each informations by numbers and then add with this is called a bias. This is called a weights. Okay, but that's just the terminology. But for us mathematically, this is nothing more than R5, right? Combination of the input. Okay, so you see that information sent from the other neuron, you do an R5 combinations, and when the difference in potential higher than some value, then you activate or fire, right? So that's why we need a function here. So this function is called an activation functions. Okay, so this activation function is going to be 0, right, or non-zero if it's over some threshold. So this is generic activation function now, and then it sends information to the other neurons. Okay, so it's amazingly very simple way of modeling our neuron, right, in our brain. Now, to do a little bit more on the notation. It doesn't need to be 0 to 1. By the way, it doesn't need to be 0 and 1, right? So we're talking about classification now, but it doesn't need to be 0 and 1, okay? So x1 on the way to xd is denoted as an input vector of the neuron. Weight, right? Weights also belong to same dimension, right? It must be the same dimension of the input vectors. Okay, the activation function typically, we don't write f. We actually traditionally we're gonna call the activation as sigma. Okay, sigma. Notice that is taken from real to real. So this is it's a scalar functions. Take a scalar and return a scalar. That's the key. And then remember that you take the R5 combination. So this is basically saying that B is equal to 0, right? This is nothing more than say that the bias B is equal to 0. Remember that we take R5 combinations and then we apply the activation functions, right? Everybody's okay with that so far? Okay. So the activation function, this should be sigma. Okay, this should be sigma. So this is the famous McCulloch. So pick Newton's neuron. I'm sorry. So McCulloch is a professor from now I forgot. I think it's Michigan. Okay, University of Michigan. Pitt himself is very interesting. He actually was a genius because he didn't go to school. He didn't go to school. And back, in this is 1940, 445 or so, in the 1950s, U.S., but in the U.S., there's a lot of abuse, right? So his dad always beat him a lot. So whenever his dad beat him, right, he run away. He went to a library and reading. So he actually read all the books from Newton, right, on Newton principle. So he trained himself. And then talk and then send information to my colleague, right? And then they become a best friends. And then Pitt actually got admitted, or my colleague recommend Pitt to New MIT. So Pitt actually got a positions because of what my colleague see from Pitt, right? And people see from Pitt. So he actually got admitted to MIT as a graduate student, right? Even though he never actually even went to high school. So he went to MIT as a PhD student, and then Matt Pollock actually followed as well as a researcher. Unfortunately, and then back to von Neumann, right? Von Neumann, everybody know von Neumann is one of the key figure back then, right? In the 50s, even von Neumann think that Pitt is highly of Pitt's, and they're waiting for Pitt's thesis to actually make a really big discovery in mathematics and neuroscience. But then, I'm not going to tell you the last part of the story. Actually, the last part of the story is quite sad, right? It turns out Pitt would actually never actually finish his PhD. He actually burned his PhD thesis, and there's some reason behind it. But anyway, it's just a quite sad story, tragic story, but behind a very genius, right? Pitt. Anyway, this is McCulloch, and Google around. Actually, there's a story writing about Pitt, the first artificial neuron for human ever, right? And then what they come up with is this activation function. If the weight or the I-5 combination, right? Theta, you see that I am not consistent here. This is actually weight. W is theta is actually the weight vector here, right? So when the input, the I-5 combination is greater than 0, like the potential is over some threshold, this threshold is 0, then it's fire information. The function is 1. Otherwise, the neuron does not fire, right? So it is 0. Very simple idea. Okay, so if you want to plot that, it's actually easy. It's just a step function, right? Everybody can see. Oh, by the way, 11:50. Okay, so we continue after this, after lunch. Okay, 1 o'clock. We continue this on neural network. All right. I see you at 1 o'clock. Okay, so it's 1 o'clock. Let us start. So before I start, I'd like to mention that I have a stucky nose, and my throat is very dry. So I don't know. Hopefully things are better, right? So if anything happen or I cannot do it tomorrow, I will let Professor Chung Hao know, and then he gonna let you know. Okay? But hopefully it's just better. But it's just a stucky nose and the throat is actually so dry. But hopefully it's better after tonight. Okay, so we look at this is the McCulloch Pick's activation function, right? It's just a step function like we mentioned. It's just simple step function that you can see. And of course, remember that in the gradient descent that we just learned, the function need to be differentiable, need to be smooth in order to, do iterations, right? This is not smooth. Of course, there's a theory on non-smooth optimization as well. So instead of using gradient, you're gonna use subgradient. So you see that there's a subgradient theory as well for, well, actually we can prove, to answer your question as well, we can prove the conversion for much more general case, right? With non-smooth but still convex function using subgradient. But again, that is something that we cannot cover here. But of course, right, the natural thing is that, okay, this does not work, so we have to smooth it out, right? So there we have the logistic functions or the sigmoid function. Sigmoid function look like that. 1 over exponentials of negative t transpose x. So theta is actually the weights, right? I use w and theta interchangeably. So that function is actually quite close. You see that it's actually a smooth approximation of the step functions. So this is something that people start in the past to approximate or to smooth out the McCulloch Pitts function. Okay, so there's many. If you Google a little bit, there's a zoo of activation function online, many of them. But there, for example, these are popular function. Rectilinear, I told you before, right? Rectilinear function is, let me see. Yeah. So this is the hyperbolic tanh functions. And this is how it look like, right? Again, it's a kind of smooth approximation of the McCulloch step function. But the ReLU function is interesting. It takes the maximum of the zero and input and the z, which is input. So basically, this function keep the positive part of the functions, right? This is z, and then this is upward. Uh, this is a max of zero z, right? So if the input is positive, it keep the input at ease, but if it's negative, it's set to zero. That's a very simple cutoff function. Okay, it's a very simple function, and by far the ReLU function is the most popular function in the machine learning or deep learning community. We can prove a lot about the ReLU functions, but less for the other activation function. There's a lot theory about ReLU. Okay, so so I'm not I'm not gonna try to go through this, but just I provide a Python code here for you to try, and that scikit-learn that you can see. You can try if you want to, right? This is iris classification flowers. There's two type of flowers, and the question is, can you classify these two? One is setosa, the other non-setosa. And I would invite you to go through. And this, you see that it used the sigmoid function as for classification. Okay, so that's a sigmoid function 1 over 1 plus exponential function right there. Right, this is the activation function sigmoid here. Yeah, and I'm gonna go through. I'm not gonna go through this. Okay, you can try later when you have free time. But let me summarize what we look at. Very simple so far, right? Nothing seems to be special, difficult, or anything. Supervised learning, there's two type of supervised learning. Um, okay, so for classification, so we look at F is from I X to R. For classification, I'm sorry, X to Y. For the first supervised learning is a classification problem. where y is have only, a number of values, for example, right, 1, 2. But this is binary classification, but you can have more categories. Okay, and for regressions, so typically y is, for example, r, right? So the only difference is that the white space, the range of the function, either continuous value or the category or categorical, right, values. And remember that supervised learning, we need to provide, both x and y, right? Xi, yi, and then we try to, and this is a given. So we are given xi and yi, like from 1 to, let's say, n, and the questions, right? Can we learn, right? Can we learn the functions, or can we approximate f, right, with a deep neural network? Okay. So in order to do so, that the family, so I just do summary of a few important point there. So we look at supervised learning right now, and we look at nonlinear activation functions, and we assume that the function is differentiable, right? Then we actually we can actually, and then we need to use a gradient descent. This is just overview, and then we go into detail in a second. So don't worry, right? This is just an overview. In order to train, or in order to learn F, we typically use gradient descent. Okay, we typically use gradient descent to learn. Just an overview of the roadmap. Okay, so I'm going to look at activation network now. Finally, we get to the point that we're looking for. So activation, artificial neural network or deep neural network is actually try to mimic the brain, or our neuron in the brain. But of course, our brain. By the way, how many neurons in a person brain? How many neurons in a person brain for an adult, approximately? How many? You want to see complexity? Somebody say something? Million? Billion? Good guess. 1 billion? 2 billion? 3 billions? Okay. Any other guess? 13 billions, approximately 13 billions neurons. Okay, so it's a very complicated thing, and we try to learn that, which is to mimic that, right? Which is difficult. But artificial neural network actually designed to mimic our neuron, and what we try to do today to learn something about it. Okay, so we're going to look at the artificial neuron again. Remember that this is just summarize that what we just did before, right? The input x1 to xd, w or W or theta is also in the same space. Okay, this is just review upon a pass it very quickly. Okay, finally we go to neural network. So this is neural network typically organized into and typically we only look at the directed graph, right? You are a mathematician, there's a graph theory. There's even class or a community about graph theory. And graph the many type, but one type is directed graph. That means every edge is connected one vertex to another, right? With an arrow, so one directions. So this output of this become input of this, but not the other way around, right? It's directed, have a direction. And in the neural network, we actually organize the neuron. By the way, each of them is called neurons or vertices, right? So the information actually go from the left to right, right? The output of the current layer is input to the next layers, and then the output of the next layer is the input to the next layer, and so on and so forth. this is typically called input layer, which is X input, right? And whatever you have in the last layer, we call the output layer. Everything else in between is called hidden layers. Okay, so what I show you here is one hidden layers. The first or the input layer have two input, right, or two neurons, and then the hidden layer, which is only one hidden layer in this case, three neurons, and then output layer only one. Okay, so important things, neural network. Of course, in our brain, we don't know things can be connected very, bi-directional, right? Complicated manners. It doesn't need to be, directed and one way this way, right? Forward. This is also called feed-forward neural network. And you can, if you do literature, you want to see why called feed-forward, because you just feed forward, right? The output as an input to the next layer and so on and so forth. By just intuitive words for that. So directed graph from left to right. The first is called the input layer. The last is called output layer. Everything else in between is called hidden layers. Okay, so we're gonna look at the neural network now, and remember that the activation function is there, right? So we still in one hidden layer in this case, right? We're hidden. In general, F or the map is from RD to RP. Okay, so in our case, the X here is in RD, and then on WI is also in RD. Okay, so, and then we just say on the bias actually 0. Okay, on the BI 0, and notice that the key thing is that sigma take from R to R, and when it see a vector, it acts, right? It act component wise. This is important. So you see that you see that you have every neuron. So this is in this case, yeah. This say we have P neuron, right? This is P neurons. This corresponding to this. According to we have P neuron. I'm sorry, what happens? We have P neuron. Okay, so and each neuron receive input, and you see one more second in a second, right? So the key thing is that activation function act component wise. When it see a vectors, it apply at each component of vectors. When it see a matrix, it apply at each component of the matrix. So that's just a convention. Okay. Really okay with that? No questions? Okay. So this is actually more graphically how it looked like, right? So the input X, on the input X here, right? You multiply by the weight 1. X means everything here, right? So this is weight 1 means that both of them here. This is the first components. This is WI1, this first component of the weights, and then this is the second component. In this case, just 1. I'm sorry, 1 here, 1, and then this is 2. So X here is actually in our case have D is equal to 2. D is equal to 2, right? But that means X is in 2. So what it does is that you take X and multiply by the way F5 transformation. Remember that, and then you act with the activation functions. Okay, same thing for the second neuron in the hidden layer. The input X. This is fully connected. Okay, so the input X also the whole vector X go to the second neuron, the whole vector X go to the first neuron, and then F5 transformation, and then act by a nonlinear activation function. Same thing, right? Same thing for the third one. Okay, so now the input X, we become input for the third neuron, right? And then it's doing alpha transformations, and then it's applied by activation function. Okay. Okay. So of course you can write as a matrix form, right? The matrix form is actually nicer. So W is a matrix there. You can write in a more succinct form. So W is a matrix whose column, each row, this is the first row is the W transpose. Sorry, W1 transpose, the first row of the W matrix, and then the second row of the W matrix is the, I'm sorry. Actually, let me actually put it down this way. It's easier. And then dot, 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 right, until WP transpose. So that's our W matrix, wave matrix. So wave matrix is a collection of the wave for all, each neuron, right, for that layer. So we are in the first hidden layer now. So you can write very nicely by sigma W, right, times X here. But what I mean is this, right? Remember that sigma X component wise. That's a key, right? Component Y again. Okay. Now, so you can write a little bit more nicer, right? Compact form for the first layers. Okay, so that's a demonstration for you. Now I'm going to generalize. We're going to generalize in the arbitrary L hidden layers. Any question before we go to a generalization? No. Okay, generalizations. This is a L layers neural network. So notice that we have L layer here. So by the way, this is let me go back here. So this is a two-layer. Typically, when you count, I mean, this is not conventional, by the way, right? It's not universal. Everybody use differently, but the very popular is to you count layer. This is layer one, and you don't use the input layer as you don't count the input layer. You only count the layer after the input layers, layer one and then layer two. So this is two-layer neural network. That we just see two-layer neural network. So now we generalize to L layers. You see that we don't count the first layer because first layer is X itself, right? And then F1 is nothing more than, remember, right? Fi or F1 first, F1X is nothing more than sigma of W, big matrix here, right? This is a big matrix, W1. Let me call this is W1. It's gonna be look similar to the other one, so maybe let's do this. W1X. Okay, you can add a bias here. It doesn't matter. To be general, then you add a bias here as well, vector here as well. Then F2 X is equal to sigma of W2 of now F1X plus B2, and so on and so forth. So it's a nested, right? It's a nested composition, nonlinear, nested nonlinear combination from the first layer on the way to the output layer, which is L layer. Everybody okay with that? Just very simple, a nonlinear composition of function in a very special way, right? The output of the previous layer is input of the next layer in an affine manner, and so on and so forth, right? So this, if you do this on the way, it's gonna be something like this. FLX is nothing more than sigma at WL matrix times FL minus 1 X plus BL. Okay. Any question? Okay. Now, this is just visually, that's how it look like. Right? You have input to first layer and then to the input, the output of the one layer to next input of the next layer and so on and so forth. Okay. So very simple. In a directed manners. This is example of two layers, right? That we talked about that before. Implementation. Actually, you can do a simple implementation as well if you want to, but we're not going to go through this. I let you do it, okay? So we're not going to go to that at all. Okay, so the neural network layer, layers, the output layers typically one, but that doesn't need to be one. But it can be have multiple output. It doesn't matter. The input layers, whatever the vector X that you have. I think there's a lot of noise, right? Maybe I'm so close. Maybe. Let me go a little bit further away, perhaps. Hopefully better. Hmm? Oh, yeah. That would be the reason. Yes. Okay. So just very simple. Okay, we need to have three terminology here, dense layers. That means every neuron of the previous layer connected to every neuron of the next layers. Right? For example, this case is a called dense neural network, right? Dense layers, because the neuron on the neuron of the previous layer or the current layer connected to every neuron of the next layer. Same thing here. This is dense. Convolutional, I'm gonna skip that. I let you do research on that. We're not gonna talk about convolutional neural network in this class. We're not talking about recurrent neural network either. Okay, so I like you to take a look. But for this class we're gonna focus on dense, right? The feed-forward neural network. Just provide you an easiest case, a fully connected neural network. That's what we want. Okay, so we can use neural network for supervised learning. You can use for not unsupervised learning as well. But we still in others we haven't gone into detail. Oh, by the way, okay, actually the question is this. Okay, you see that, right? Actually, this is a good one here. So far, I show you the structure of neural network. The thing that are unknown to us is what? Of course, the number of layer you pick, we pick, right? The number of neuron on each layers, we pick. But these, right, weight and biases for each layers are not something that we can pick, right? Because we want the fx there, the output of a neural network is close as possible to the function, the underlying function that we want to approximate, right? So we cannot just pick arbitrary W. We actually, in reality, we cannot pick arbitrary number of layer or neuron either, right? But let's suppose that we can choose the number of layer, we choose the number of neuron on each layer. What remains? What remains is to determine the weight and biases, right? So thinking about training is training, but that's why I call training, right? Is nothing more than just adjust. You adjust the weight and biases for each neuron here, so that our functions, our neural network is actually can approximate your the underlying unknown function well. Okay, so that's in the big pictures. Training is a way to adjust the weight and biases so that we can match all we want to, we can, so that we can have our network to be as close as possible to the function that we're interested in. Okay, and how do we adjust the weight and biases? We use gradient descent, right? We're gonna talk about that maybe yeah, next tomorrow. We're gonna talk about that. I'm sorry here. So in practice, we're gonna actually optimize. I'm gonna go to detail about that later. Okay, so don't worry. I'm just give you a general big picture right now. The way we adjust the weight and biases for each neuron, each layers and each neuron is to use gradient descent, right? Because gradient descent is you see this is how we adjust, right? Let me go back here. Gradient descent. Where's our gradient descent? Oh yeah. You see the blue or the green? You see that? It's our gradient descent here. So X is now weight and biases. You can think about that way right now, just like one step ahead of the futures. So this is weight and biases, all weight and biases. How do you update it? You take the gradient, and then this is a current weight and biases that we choose. This is the next bias and ways that we choose. So we use gradient descent. But don't worry, we're gonna go into that detail later, okay? So right now, I just want to show you generically the way. So we see the topology of the neural network already. What remains is how to determine weight and biases. And we're going to do so using gradient descent. How are we going to do that? Let's wait. Okay, this is just a broad map for us. Okay, so let's talk about pro and cons for now. Pro and con neural network. Actually, it's very powerful. It's flexible. It can actually approximate any function. We're going to do that next. So this is what we're going to do, right? This is a universal approximation theorem. So if we want to use a neural network, we need to know that this is true, right? Because our function that we want to approximate, typically we don't know. Thinking about, if you want to monitor the temperature distribution in Taiwan, right? Given the current temperature distribution, what is the temperature distribution tomorrow? So we have input, but we want to know what is output for tomorrow, of course. That function you don't know, right? Um, so if the neural network can approximate any function well, then there's a hope that we can use neural network to approximate things that we don't know. If we can prove that, right? And that is exactly what is our next goal. The neural network actually work well for unstructured input like audios or images. Actually, you can do voice recognitions, right? That's what audio images, classification of us. Like I mentioned to you, I was in the airport flying over here. Just take a picture of me and know exactly who I am. They can achieve the state-of-art performance of any method out there, right? Including traditional math methods. But there's a lot of drawback, a lot. I just provide you two here. Can be slow and hard to train, right? Why? Because you're thinking about this, right? Okay. The number of weight and biases can be huge, right? Depend on how many layers that you pick and how many neurons each layers, right? Because each layer itself have unknown weight and biases. So the number of weight and biases can be huge. So you have to do optimization problem in high dimension. So that's the first thing, right? Difficult. So the landscape, the log, you're gonna see, we talk about that later. Second, it's very, very nonlinear. You see a nonlinear composition, right? Nonlinear or after nonlinear composition, very nonlinear functions in high dimensions, not convex. I will remember that we prove the kind of gradient descent convergence based on convexity assumptions, but there's no way that it's actually convex, right? Because the sigma function itself is not convex, as you can see. The sigmoid functions, let me go back here a little bit, I'm sorry. There's no reason why the sigma function is here, right? It looked like this. We looked at it before. I think I shouldn't do this. Yeah, this look like that, right? It's not convex, nor concave, right? So the deep neural network itself is not a convex function. very nonlinear and very high dimension. So very, very hard to train. Could be very hard. It requires a lot of practice. Okay, this is where the art come to the pictures. We can have the mathematics, but the art and experience is necessary for doing deep learning. Okay, and large network require a lot of data. In other words, if you have a small amount of data, you shouldn't do large network. You don't do very deep. You don't do very wide, right? The reason is this: the larger the network, we're gonna talk about that later as well. The larger the networks, the more function approximation capability it is. It can approximate any function, right? Because it's so expressive that it can overfit the data. So if you have small data, you don't want your network to be so expressive, because if it is, it overfit the data, and then the prediction is going to be very bad, right? So if you have a small data, you use small neural network. If you have larger data, or if you want to use bigger neural network, you need more data in order to train it, right? Without compromising the bias and variance trade-off, bias variance trade-off. We talk about that later as well. Okay. Again, this is just a very quick overview of how neural network look like, right? Some pros, some cons of the neural network. Okay. So any questions? Sorry. Any question before we move to universal approximation theory for neural network? So we're gonna look at that part only, right? We're gonna talk about bias variance trade-off after we actually learn probability theory a little bit. Okay, so now we're gonna look at, we forget about gradient descent as well, right? Because if theoretically a neural network can approximate any functions, then hopefully the gradient descent can find a good one, right? So before we're talking about training the neural network, we want to make sure that neural network can be, can be used to approximate any function well. Okay, so any question before we move to the next part? Okay, so let me move to the next part. Okay, so actually no, let me view. Okay, so I'm sorry, I forgot about that. Okay, so this is universal approximations for theory for ReLU. We restrict ourselves to one very special case, which is the ReLU neural network. Okay, because that's the easiest one. And for this short course, right, only 1 week we are together. We don't want to do something complicated and too technical, right? Something easiest. Even that, you see, right? It could be technical, depends on how your background. But I promise you, I'm going to use very fundamental ideas, calculus. We only use calculus to prove that. Okay. All right. So recall this is the ReLU active rectilinear unit activation function. How it look like? Keep the positive. Set the negative to 0. Okay. So let's do some mental work. Mental arithmetic. If I had a function, okay, so we notice that the ReLU function is a piecewise linear. Everybody okay with me on that? It's a piecewise linear function, right? So the question is that if I have a piecewise linear function like this, can I approximate, can I exactly represent that piecewise linear function? That's a piecewise linear, right? 0 and then x minus a times the slope r. Can we construct a ReLU neural network to capture gx exactly? Of course, right? We expect that, yes. And what is it? Very easy, right? Very easy. So max of x minus a, 0, right? Allow us to deal with this case, right? So if x is greater than a, if x greater than a, then this is x minus a. And you multiply by r, you are here. If x is less than a, this is 0, time r is 0 as well. So we actually can recover our function easily, right? So this is equivalently to this. But this is nothing more than the ReLU activation functions. Oh, I'm sorry, ReLU, one single ReLU. This here how it look like. I'm sorry, actually, let me delete it a little bit. So this is a one single hidden neural network that can represent this function exactly with ReLU activation functions. So the input, the weight, you see that the weight here, weight W and bias is negative A. Everybody see that? So weight times X is minus, that is X times 1 is X minus A, the bias, right? And then you apply the sigmoid, apply ReLU activation function. So this is just, by the way, this is a kind of, the usual way to denote a neural network. Each neuron, not conventionally, right? You put the weight on each connection and you put a bias on each neuron. Okay, so this is the bias for this neuron. This is the weight connect from the input to here. So when they come here, it's X, it's minus A, and then you apply the ReLU. This is exactly the ReLU. Everybody see that? For X minus A, this is Z. I remember the ReLU is maximum of Z0. ReLU is maximum of Z0 or 0Z, doesn't matter. That's a ReLU. So, and then after that, you multiply by the output of this guy, which is now this, multiply by the weights. You have zero bias here in the output layer, right? Because there's zero bias here. Everybody see that? So this neural network represents that function exactly, what we expect, right? Because that function is piecewise linear. Okay, now look at asking you a more interesting question. How about that's a hyperplane or just a linear? For the linear function is a special case of piecewise linear, right? So we should be able to represent the linear function exactly using ReLU. This is a kind of just warm up for you, right? And can you do that? And the answer is yes. The answer is yes. It turns out that the linear function is a combination of two ReLU, right? Two ReLU here. Maximum AX plus B 0 and then minus of AX plus B 0. I invite you to check on that. I invite you to check on that. This is exactly AX minus B, okay? And because of that, this is exactly the neural network can represent that function exactly. Look at this. This is the input X, right? So you have two neurons, one and two neurons. The first neuron, you multiply by the weight A, and then add a bias plus B, and apply your activation function. The second neuron, you multiply by the negative A weight, and then minus bias B here, and then you apply the ReLU. That exactly this. And then the minus operation here is what? This is output, right? This is output of this guy. This is the output of this guy, right? This difference is nothing more than one, right? The weight multiplied by the output of this one, which is this. One times this is this. Negative one times the output of this. You see which is the output? Negative one times the output is this. And then zero bias again. And then this is nothing more than the AX plus B. Everybody okay with that? A very simple check, everybody. So again, we have constructed a single layer neural network to approximate the linear function exactly using ReLU with two neurons, two layer and two neurons. Okay, this is a more interesting case. This is a more interesting case where you have really piecewise linear function now. Okay, so we have this is the truly piecewise linear function with m knots, basically m breakpoints, right, where the piecewise linear move to another one. So we have m of them, and of course you have two different slope here. Okay, the question is that can we approximate these functions exactly using Relu neural network? What Relu neural network actually can approximate this function exactly? Okay, so we have total m plus 2 informations, m breakpoints, and 2 slope at the end, right? Without the slope, you don't know. You cannot determine the function, right, uniquely. With 2 slope and m breakpoints, we have a unique piecewise linear functions. So we have m plus 2 informations. So we expect that a neural network have m plus 2 unknowns as well. Okay? So there's a couple of pieces here. So the first one is sigma x minus ai from 1 to m. Okay, so notice that each of them look like this. So this is x here, this is ai, and then this is our our Relu functions, or sigma x minus ai is noting that in the maximum of x minus ai 0. It look like that. Okay. So at each xi, you have one Relu function, and then we're gonna sum them up. Because a piecewise linear function, of course, if you sum two piecewise linear function, you get another piecewise linear function. So we construct that first. So for every breakpoint, we put down Relu. We don't know this, right? But we actually determine the weights. One here and the bias minus I here. Okay. Now we need this. We need this term because we need that term because if the slope, if A1, remember that A1 is somewhere here, right? A1, the slope at A1 can be like this, the function itself, right? The slope could be like this, or the slope could be like this. They're positive or negative. Okay, so especially if the negative one is okay. I'm sorry, the positive one is okay. The positive one is okay, right? But the negative one, if you just use x minus a1, you remember that in this case we have x minus a1 here. That term captures this guy, but it does not capture this, right? So we need this to capture this case in case our function actually have the slope at the left hand point this way. Everybody okay with me on that? This, because these functions look like this. Let me. So this is sigma of a1 minus x. Okay, so it allows us. So we add more. So of course, if our function is like this, then c0 equal to 0, right? If it's like this, then we need c0 non-zero in order to determine it. Okay, another thing is that another thing we need h here. We need h here. Why? Because if we look at this, right, and if we evaluate at GA1 without this, right, without this, f of A1, which is here, all of these guys, what is sigma of A1 minus AI? What is it equal to? for any I. Like for example, this guy. What is the value of this red function at A1? What is it? 0. Clear, right? That's 0. Okay, so all of these guys are 0 for A1. So without this, and of course this as well, like this, when x equal to A1, this is equal to 0 as well here. So without this one, f of A1 equal to 0. And we cannot deal with the case where our function is like this. If we want to approximate this function, which is the function value at A1 non-zero, see that? This piecewise linear function, the value at A1 equal to non-zero. So we have to add, some constant here to actually to take into account or to take care of the case when the function that you want to approximate evaluated that A1 is non-zero. So now we cover everything, right? And let's count. Now this is what we do mathematics, right? We have m plus 2 informations. Remember that? M breakpoints, 2 slope, m plus 2 information. How many variables here? How many unknowns here? M plus 1, m plus 2. So m plus the unknown. So there's hope to solve for these m plus 2 unknown uniquely with m plus 2 informations. Everybody okay? That's the first thing that you do when your advisor asks you to solve some problem. If he gives you m informations, right, and or she give you m informations, and if he or she give you more than m equation or less than m equation, you need to ask him or her to check again if we want to have a unique solutions. Okay, so this is good because we have exactly the number of unknown, not the number of equations. Now, how do we determine these unknowns? Okay, so this is our function g. This is our just a linear combination of ReLU, right? Activation functions. Okay, so we just set up m equation, solve for m unknowns. At x equal to a1, f a1 must be equal to g a1, right? Because we want to match exactly, right? So g a1 is something that we suppose we are given. F a1 is equal to h, right? So the first equation immediately tells us what h look like. H must be equal to GA1. Done. Solve for h. Now I'm going to do this. Look at A2. X equal to A2. F of A2 is equal to what? Of course, F of A2. What happened to this? Sigma of A1 minus A2 is equal to what? Equal to what? Remember this guy look like this. Equal to what? 0. That's correct. Right? So that's why you don't see the this term here. This term actually is 0. Okay, sounds good. Now, amongst this sum, it turns out there's only one term at non-zero. The other term actually is 0. Right? Because remember that we look at this. If the ReLU function is on the right, anything here is going to be 0. Anything on the left going to be 0 if you look at this function here, right? And you are at A2. If you are at A2, the only activation function is non-zero is sigma x minus A1. Everybody see that? Do you see that? Okay. Okay, so let me actually do this. You see, so maybe do A2 here. And then this is A3. Okay, so this is sigma x minus A3. Okay, I'm at A2 right now, right? Of course, sigma x minus A3 is 0 on the left, non-zero on this side. So this function is 0. sigma x minus A4 will be like this. So it's also 0 at A2. Everybody see that? So the rest is 0. The only one that's non-zero is sigma x minus A1, right? Because sigma x minus A1 look like this. Which is sigma x minus A1. Everybody see that? So when you evaluate this at A1, this is going to be something like that big. Good? Oh, I'm sorry. It's actually overtime. Okay. That's the second equations. Of course, h is what given, right? So in this sum, this is 0. Only one term non-zero, which is this. The rest is 0. And so on and so forth. We continue tomorrow, everybody. I see you tomorrow.